Thanks for tuning in to Stay Sharp with Razorleaf, your secret weapon for all things digital in products and manufacturing. In this episode, Jen Farello is joined by our CEO of Razorleaf, Eric Dubell, to unpack the concepts around digital twins and virtual twins. They are joined by Ramesh Haldorai, who's a well-respected PLM industry veteran and is the Vice President of Strategic Consulting for the 3D Experience platform at Dassault Systèmes. Ramesh outlines the various types of virtual twins and their benefits. While the various types can support different parts of the design and manufacturing process, Ramesh emphasizes that businesses must focus on solving the business problem first, and then take incremental steps to gain the most value from a virtual twin. Let's listen in.
Welcome back, everybody, to Stay Sharp, the podcast about all things digital related to products and manufacturing. I am Jen Farello, and today I'm joined by our CEO, Eric Dubell.
Hey, Jen. Thanks for having me.
No problem. And today we're going to explore the topic of virtual twins. Joining us today is Ramesh Haldorai. Is that correct?
Yes, Haldorai.
Okay. Ramesh is the Vice President of Strategic Consulting for the 3D Experience platform at Dassault Systèmes. Ramesh, can you please share a bit about your experience and your work at Dassault with our listeners?
Yes, hello everyone, and thank you, Jen. Thank you, Eric, for having me, and Julianne. Yes, I've been with Dassault Systèmes for more than 20 years now. I've been all along in the PLM domain. I started off early on with CAD and moved on to PLM, and now with the 3D Experience platform. I'm based out of Boston, and I've visited many of our customers here, and glad to be on this podcast.
And we're happy to have you. Excuse me. So before we get started, I wondered if one of the things we try to do on the podcast is kind of level set. So, by starting with like a definition, et cetera. So can you tell us a little bit like when we're talking about a virtual twin, what is a virtual twin? How is it different than a digital twin?
Yes, that's a very important question, Jen. And I think we need to really understand this clearly. And for doing that, maybe I'll take a step back first and then look at how we got here, how we got to where we are today with the 3D Experience platform. As you know, Dassault Systèmes has provided CAD solutions for 40 years now, and we have gone through an evolution process. We went from CAD to providing a PLM system, and then when we had the PLM system, we integrated multiple tools out there like CAD and CAE tools before we generated the 3D Experience platform. So 3D Experience platform was a major investment, and what we really did is rebuild all the siloed applications on top of the platform. And what this allowed our customers to do is to help them seamlessly go from design to simulation, design to manufacturing, design to service, all on a single platform. And that brought about a big productivity boost for all our customers. Now, the next step is to really understand what they can do with the platform in a way that it is seamless in the design organization itself and across the enterprise. So let's think about a situation where a designer is working in an organization, for example, a mechanical designer, and they are working on 3D Experience platform. And then the electrical engineer is also working alongside, and there's probably a software engineer working alongside. When three of these designers are working and building the systems that they are building, they have to communicate with each other and make sure that whatever they are doing is helping each other design in a way that there's no rework. So this is a difficult task unless they have a definition up front which tells them what are the clear requirements or what are the systems and how do they communicate with each other. So they had to define a functional definition of what these systems would do upfront. And that brought about not just about what the product looks like and how it fits, but also how it works. So they had to define how it works upfront. And this was called model-based system engineering. So they got into model-based system engineering, defined the different systems, what are the interfaces between the systems, what they're exchanging between the systems, and how these systems communicate upfront, so that when each one of the different disciplines build the different systems, they all fit together seamlessly. Now, because of doing this, what we are able to achieve is to be able to simulate not just how the product looked and how it fitted, but also how it worked. And that, if you evolve that in all the different multiple disciplines and 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 give the opportunity for everyone in the organization to see what the product looks like, how the product fits, and how it actually works, is the first step of the digital twin. So customers are working today to achieve that first step. Now, there are two more steps that I want to go through, but before that, I want to pause and see if there's any additional comments from Eric.
So that's the definition of a digital twin, but a virtual twin is more than that then? Or are they synonymous? Because I know a lot of folks I talk to consider them virtually the same thing.
Yeah, there are many definitions of digital twin out there, and one of the more common definitions is collecting data from existing systems and being able to analyze the data and see how the system works and build, let's say, machine learning models out of the data that's collected. But that's I think is a definition that holds good for an industry where there are large capital assets, for example, a power plant or a petrochemical plant, and you want to know how the systems are behaving, and you want to optimize those systems. So that's one end of the spectrum. There's also a definition of digital twin similar to what I explained, except that it is more, let's say, a fit and form. That's the 3D definition of it, and not really how it works. So how it, in order to know, do for the twin to behave like the actual system, it needs to have the underlying definition of the physics models and the digital systems model inside, and that's what makes the difference between the digital twin and the virtual twin. So that's step one, right?
Because a lot of times I think of it as a digital twin as something that the physical entity exists and you're replicating the physical entity to be predictive, but a virtual twin is something that doesn't necessarily exist yet, and it's all virtual. The product maybe hasn't even ever been built yet, and you're trying to use it to simulate what it will look like when the physical entity, physical whatever it is, actually gets built.
Correct, and that's a very important point because the virtual twin does exist before the physical replica exists. The physical instance is the replica of what you build digitally in the virtual twin. In the digital twin world, they usually call the digital twin the replica of the physical item. So I think you should think of it in reverse. So we build the virtual twin first, and then we get a replica of it, which is actually the instant of it. Let's say it's an instance of that is a physical product. So once we have a product which works, now obviously the benefit of this is that customers can reduce the number of prototypes that they make. So imagine that the people from different disciplines are working together on a complex product like an automotive. Then usually to figure out how the product works, they need to go and physically build these parts and test the physical prototype. And the virtual twin is good enough to do all the testing. Obviously, you will probably have a physical prototype at the end, but not near as many you would have if you didn't have the virtual twin. So reduction of the number of prototypes means reduction of cycle time as well. So that's the benefit from the virtual twin.
You could be a lot more proactive as opposed to reactive that way when you're designing your products. But is it to do all that then? Do you need model-based systems engineering required to really get to a virtual twin then?
Yes, ideally you will have to have model-based system engineering because model-based system engineering and finite element modeling and simulation would give you the basis to figure out how the product actually works. So that's kind of like a step before we create a full virtual twin. But customers can come at it from different angles, let's say different dimensions. Maybe they can start with the 3D and then build a complete 3D definition, which is as close to reality as possible. That will allow them to anticipate issues that can happen in the shop floor related to form and fit. And if they build the complete model-based systems model and the finite element model and incorporate it into the virtual twin, then they'll be able to do virtual testing and virtual commissioning, actually see how the product works. And that brings me on to the next step in the virtual twin, which is basically taking the virtual twin that you built and test it in the real world condition. For example, if you are developing an automotive, how do I take the automotive and make it and drive the automotive in the real world condition and test the ADAS system or see how it behaves in real world conditions? So that is the second step of the virtual twin, which is um, which is designing and simulating what the product would feel like in real world conditions.
So simulating is the key word there, right? Because it all starts with the simulation. If you can't simulate it, since you don't have a physical anything physical yet, there's no way to really create a complete virtual twin.
Yeah, simulating is an integral part of modeling. I think today, one of the things that is very important is to have the capability to both to model and simulate for every engineer in the organization. Because in the past, maybe a decade back, it was all separated. We had different engineers for who modeled and different engineers who simulated. But simulation is becoming an integral capability of the design environment today. That's correct.
So, aside from virtual prototyping and some of the simulation, what are some other things that you can do with a virtual twin? What other benefits does that bring?
Right, and when customers build the virtual twin and they're able to reduce the number of prototypes and identify issues early on and cut down the cycle time, and then take the virtual twin that they build and build the virtual environment, the virtual customer environment, and test it in actual customer condition, they can figure out how they will commission this product in the environment of the customer. For example, if they are building something that goes into a power plant, then they can operate this equipment in the power plant. Let's say it's a generator, and see how the generator will work in the context of the power plant, and identify what is the exact requirements of the customer based on the exact replica of the customer environment, and then anticipate all commissioning issues upfront and resolve most of the issues that you have when you actually visit the customer and you're installing the equipment at the customer premise. So that's the advantage. That is the next step after you've reduced the issues that come early on in the product development lifecycle, and now you're reducing the issues that come during the erection and commissioning of the equipment. So that's the second step, and I think that leads me on to say what is the third step. The third step is is basically making a virtual twin of your factory, right? The manufacturing facility. How do I define my process and then simulate my process and get all the equipment and resources I need in my factory, lay out those equipment according to the process definition, and then make sure that the product can be manufactured, the product and all its variants can be manufactured using that process on that assembly line that I built. So that can be done completely virtually. And obviously, the benefits here is that you're able to anticipate all the issues, production issues that you might have upfront by simulating the entire virtual factory working before you even go and make a single change in your factory shop floor.
So you would extend then the virtual twin outside of just the physical product that's being produced to also a virtual twin of the process used to produce it, as well as a virtual twin of the facilities used to produce it.
Correct. So virtual twin of the product itself, virtual twin of the product working in the customer environment, and then virtual twin of the factory where it is going to be produced. So those are the three basic components of the virtual twin, if you will. All this together helps the customer build the product and then simulate the product in the customer's environment, and then simulate the manufacturing process so that they can get the cycle time reduction overall from start to finish.
That's a lot of virtual twins.
So in the fourth stage of the virtual twin, the product is in use. So the product is used by the customer. And because the product is an intelligent product, you're able to collect the information from the product through its sensors and see if all the actuators, that is actual product behavior, is working according to the predictive models that we put in place. So we collect the data from the actual working of the system, then we build models based on the data that we collected, and we compare and correlate these models with the predictive models that we build upfront in the product development process. And this gives us a clear understanding of whether the product is behaving according to how we predicted it will behave.
Right. So I imagine that gives you the ability to kind of a closed loop feedback. So it allows you not just to determine if there are any problems anywhere along the line, but where those problems are and how to correct them. I'm curious, like I said earlier, that's a lot of virtual twins. Do you have, I mean, it seems like an ideal that you've got, you're a virtual twin of the product, of the product in use, and the product being produced in a factory. How do you have customers doing all of this?
Yes. So if you really step back and analyze what customers are doing, they are doing most of this already, right? If you look at IoT, they're collecting information from the product already. If you look at building the predictive models upfront, most of our customers have finite element methods where they are simulating the product behavior. And if you look at the manufacturing shop floor, many of them have used some kind of process modeling system to model the process. So the idea behind the virtual twin is, how do we get all these different aspects that is done by different organizations within a company in a way that it all makes it into one place, and it's all connected in a way that we can simulate that entire environment, the product environment, the customer environment, the factory environment, and finally the product and use environment. So this is not something that customers are not doing today. They are doing it today, except that they're doing it probably in a siloed manner.
I think what you're saying is that virtual twins do exist and have existed. They're just not as connected as the optimal vision.
Correct.
Not currently.
Yeah. And that's why the platform is very important. Having a single platform to be able to do this will help them create the virtual twin, right? But once you create the virtual twin, then the experience of everyone in the company changes. For example, if you talk about an engineering change, for example, if a new customer comes with a new requirement and you have to change the product to suit this new customer requirement, then typically in the past, you would be running this engineering change process primarily in a document-oriented way or in a way that it is not seamless. So imagine that you're able to run an engineering change process on a virtual twin. So that we call that a virtual twin experience. So every process that you have, for example, a defect resolution process or a configuration management process or a engineering change process, all these processes that you carry out, imagine that these processes are not just running on a document-oriented environment, but on the virtual twin itself. And that becomes a virtual twin experience. And that's when the entire organization will benefit from having this virtual twin, including customers and suppliers.
So, Ramesh, with a lot of things, you can implement pieces of it here and there to, and then step yourself into it if you can't do all of it at once. But it seems to me that, at least with the virtual twin, you need to follow the sequence of the steps. That you get much less value if you simulate the shop floor before you've simulated the product and the customer environment. And similarly, you can't really simulate the product in a customer environment unless you've simulated the product first. So it seems that these steps need to be sequential to really get the value out of them. Is that accurate, or am I missing something?
Yes. So you have to simulate the product in order to simulate the product in the customer environment. That is definitely true. But in terms of the manufacturing shop floor, I think my thoughts are a little mixed on that. Maybe there are some situations where the customer's problem is on the shop floor side, that they have a ramp up problem and they're trying to optimize the shop floor. And maybe in those cases, it makes sense to go and build the virtual process and the virtual factory layout and simulate the manufacturing facilities first before we have a complete simulation of the product. But even for that, you will need a complete definition of the product, maybe not a complete simulation model or a complete product virtual twin, but you will need the definition of the product so that you can assign the product and the various components in the product to the manufacturing process and execute it on the shop floor.
And for people who've started with a digital twin and they've got maybe someone who makes a thermostat, for example, and they have that feeding information back in IoT, that doesn't stop them from going back to the beginning of the process and virtually creating and catching up to the digital twin and encompassing that in the virtual twin, correct?
Yes, and this is a more difficult process than it feels like, because imagine you have a motor and then you're collecting the speed of the motor on a regular basis. So there could be as many as one reading per second. So every minute you're getting 60 inputs. So this is the actual behavior of it, and you can plot it and collect all this information. But the real signal there is whether the RPM is going out of bounds or not. If you have a certain bound, let's say the RPM should be between 6,000 and 7,000. And as long as the equipment is operating within that RPM, the data is not very relevant. But once it goes out of that operating condition, then that's when you get a signal. So you have to be able to get this data, and you don't need all the data, and you have to be able to get the signals out of the data, which are important for comparing and correlating with the product itself. I'll give you a different example. Imagine that you're running a shop floor which is completely automated. For example, a process plant where you're, let's say, making a drug, and you've got various parameters, process parameters that you're setting for all the equipment, and you have a certain predicted range for the outcome of these processes. For example, if you set a certain temperature level, then you're going to get a certain level of hardness in your product, let's say. So you're measuring the hardness, and you're expecting a certain hardness based on the temperatures that you set. Now, the signal for you is when the hardness goes out of bounds and it's not in the acceptable range. So for this to happen, first you need to know that the temperature that you're setting is impacting the hardness level. So you need to have that correlation. And then you need to know under what conditions, even though the temperature is set to the right point, is the hardness going out of bounds. So then you can figure out, do some root cause analysis and figure out what are the other things that are causing the hardness to go out of the bounds. So you need to have a way to go back and forth between the actual environment and the predicted environment in a way that is seamless. So it's collecting a lot of data and then making graphs out of it is a lot easier today than it was before. But getting the insight and figuring out what are the optimal process parameters or optimal product set points that you're going to use is a much more difficult task than just collecting data. So it's beyond IoT, I think.
So one of the areas where I think that comes into play is MRO, because I think a lot of people think that once you've got the physical device, that then it's just interaction between IoT and the device and changes you make. But in an MRO environment, if you're doing maintenance on a plane, it applies just as much during the design as it does during the maintenance to run those processes and run those changes through to see how they're going to impact, the product as you change it. So I think that, MRO or even change processes, it's important to keep in mind that the virtual twin lives on through the life of and modification of the product.
Yes. So there are two important points that we made. One is that even during the MRO stage, when you collect information, for example, you're collecting warranty information and you're collecting information about failures, usually in most of the industries, even before you put a system into operation, you are building models, failure models, and saying, this is my model. Let's say it's a bathtub curve, or it says when the system is going to fail, how many cycles of operations would it withstand before it fails, and that predictive model is already built. So engineers know how a component is going to fail, and the real signal for them is to know when it fails beyond their predictive capabilities. If it fails elsewhere, then they need to know that, and it becomes very important for them to understand what was that failure pattern and what led to the failure pattern, and incorporate that failure mode in their design activity. So that's the first point that I think is very important. The second point is, what if analysis. So, when you're operating equipment and you get various signals from your product, then maybe you have a situation which was not anticipated. For example, there could be a leakage or an oil leakage in the engine, for example. And then being able to take the virtual twin and then induce this operating condition, that means the fault condition, and then see how the system will behave under this fault condition is very important. And that is something you can do. You can do what if analysis and figure out how the system will behave, even under conditions that were not anticipated in the first place. So that's also very important to the engineering organization. So that improves the robustness of the product.
So, Ramesh, how would you suggest people get on the right path to virtual twins? So let's assume that companies doing some level of digital twin with some IoT now. They're obviously using CAD design tools. They're doing some level of simulation, whether it's integrated with their design tool or whether it's a separate department with separate tools. Because there's a lot of things we're talking about. We're talking about shop floor and process simulation. We're talking about model-based systems, engineering and design. All of integrated platforms. All of these things take a lot of time, a lot of resources, a lot of money sometimes to incorporate. So how would you suggest people start on the path?
Yes, so that's I think the most important question for today. Is first I would say that like you said, this is an investment on the customer's part, and before they go and invest in a particular capability, I would always recommend that they do a analysis of the value and do an assessment and figure out what is the potential benefit from the activity. For example, if a customer has got product related issues in the field and maybe the warranty cost is too high, then they have to speed up the defect resolution process. And there might be a metric that they have in terms of how much warranty that they're paying today, what is it costing in terms of customer excellence for them, in terms of lost customers because of these issues, and take an assessment of that and figure out if they invest X amount of dollars, then what will be the return and how fast can they achieve this reduction in defect resolution. And that time frame is very important. So if the time frame is fixed, let's say they need to get results within 6 months or a year, then based on that time frame, we need to decide, help the customer decide actually what capabilities they should incorporate immediately to achieve that benefit in that 6 months to a year time. So that I would say is the first step that we need to take. And depending on what problem that they are trying to solve, I think the recommendation should be made on what are the solution set that they should incorporate. And maybe they have all the solutions today. They just need to connect it and make sure that they adopt a platform approach to it. So then they may have to upgrade the systems from the older version to a platform version, not really replace the system, and help them adopt the platform and solve that problem in mind. So, end of the day, the virtual twin is going to help them solve a business problem and generate returns based on solving that business problem. And I think it is upon us to help our customers understand how to get there depending on what problem they're trying to solve.
Okay, this may be a topic for a future session, but given the, I guess, the importance of model-based engineering and design to the process, that's usually one of the bigger hurdles to overcome because it's a different way of thinking about your product design than maybe a lot of companies are dealing with. Can you take advantage of a lot of virtual twin stuff without doing that? Can that come later, or if that takes longer, does that impede your ability to create a virtual twin?
Yes. So model-based system engineering has the most benefit when the product is a multidisciplinary product. So because model-based systems engineering allows you to do multidisciplinary definition and simulation upfront. And especially when you have digital components in it, and plus the physical components, and which could be mechanical, electrical, piping, wire harness. A lot of disciplines could be to be part of that upfront simulation. But if their product is they are trying to optimize on the mechanical aspects of the product, then if they're doing finite element analysis today, so that's a good place to start. If you wanted to do just the mechanical discipline and start there and understand how they can build a virtual twin with the complete mechanical behavior understood.
So it is possible to have, I guess there are different levels of completeness with the virtual twin then. So people can take the systems engineering stage and they can implement that later or over a longer period of time and more quickly create parts of virtual twin, maybe the mechanical parts or the other things, using and integrating the tools they've got today then. That's what you're saying.
Correct. I mean, theoretically, it's possible to do that, but I would recommend that they at least take a definition of the virtual twin with all its disciplines. But when it comes to implementation, they can probably start with discipline by discipline, if that allows them to change faster.
Okay.
Well, I liked what you said earlier, is that basically where you start and how you proceed is based on the business problem you're trying to solve.
Correct. So I think that's the underlying thing for anything that we do today in 3D experience.
I would agree.
I think you're right. Well, I want to be cognizant of our listeners' time, and I think we are about up there. We did cover a lot of different topics today, not just the difference between virtual twin and digital twin, but the types of virtual twins, which was news to me. I figured there was like one virtual twin, but no, there was product, there was process, there was the product in the customer environment and in the manufacturing environment and the manufacturing environment itself. So we also touched on some of the technologies involved and how to get started. And like I said, the important thing is basically, as far as where to start, you can go incrementally. Take a look at your business processes and the problems that you're trying to solve. So, any last remarks, Ramesh, before I completely wrap up and say goodbye to our customer or our listeners today?
Yeah, I think you summarized it well, and it's. I think many companies today know about the capabilities of the virtual twin, but they have like a writer's block, right? I mean, where do we start is an important question. So I think if we can help companies start on this journey, then it will definitely has the benefits moving forward.
I agree. So I want to say thanks, Eric, for stepping in when Jonathan's out hiking the Appalachian Trail. And thank you to our guest, Ramesh, for joining us today. And as a reminder, if you have any questions based on today's podcast or something that we didn't cover or you'd like to see us cover, reach out to us on social media with your questions or comments. We'd like you to be part of the conversation. And until next time, stay sharp.
Thanks, Jen. Nice to see you again, Ramesh.
Thank you, Eric. Nice speaking with you, Eric. And thank you, Jen.
Thanks for being here and listening to this episode of Stay Sharp with Razorleaf. If you have any questions about this episode on AI and data science, we'd love to continue the conversation. Just leave us a comment on our post or send us an email at podcast@razorleaf.com. We appreciate all the feedback we receive from our listeners, so don't be shy. Make sure to subscribe to our podcast on your favorite podcast platform or on our YouTube channel. Until next time, stay sharp.